Okay. Oh. All right, here we go for the last time today. Uh, Thanks for sticking with me. You all have coffee. I told you you'd need it. Um, so in this talk, I'm going to talk about something pretty different. In the previous talk, we mostly covered unsupervised learning, supervised learning, I would say typical machine learning problems. Now we're going to look at something slightly different. It's called reinforcement learning, and I want to underline it's only an introduction. I'm going to scratch the surface, try to give you the basic understanding of what that thing is, how it differs from other types of learnings, and show you some examples based on the reinforcement learning features that were introduced in SageMaker. So you're not going to turn you into RL experts. I'm not one myself, but we're going to try and see, what this technique can do, and what the use cases are, and what the important ideas are. Okay. So, need to plug this in, I guess. So, we're used to. Here we go. We're used to supervised learning and unsupervised learning. Okay, so supervised learning is simple. You take a machine learning algorithm, you run it on a labeled data set, and you try to extract patterns. Okay, so labeled data set means samples plus ground truth. Okay, and if you saw the ground truth demo I did earlier, labeling those images, okay, that's exactly what I'm talking about. Okay, telling the model what the data set is, what each sample is. Okay, so this is a dog, this is a cat, this is a guitar player, etc., right? So classification is an example of supervised learning, and we do that a lot. So unsupervised learning is just working with the data set itself. Okay, we don't know what the truth is. So we just apply a machine learning algo to the data set, and we try to find some patterns. So for example, clustering is an example. It is an unsupervised learning technique. Okay, let's say you have 100,000 customer transactions, and you want to group them in 3 groups because you have the intuition that you have 3 types of customers, like entry level, mid level, and premium customers, and you want to figure out, okay, can I actually see this in the data? Yes or no? And maybe it's not 3 clusters, maybe it's 5 in the end, but okay, you can run those algos and figure it out. Topic modeling, we talked this morning about Amazon Comprehend that builds topics from vast collections of text documents. Okay, that's the same. Just throw the documents at Comprehend and tell it how many topics to build, and it's going to try and do that. Okay. So now, if we look at those techniques in a different, with a different angle, how much training data do they require, and how sophisticated do they get? So supervised learning typically requires tons of data, right? You've heard this before. Deep learning models, throw as much data as possible. There is no such thing as too much data for deep learning models, it seems. Some people will surely disagree, but the general knowledge is, okay, the more data, the better. And they can get extremely sophisticated, right? Again, the high level of services like recognition and others, and Poly and Translate, they get really, really close to human level of performance. Okay, that's what sophistication means here. How close do we get to what a human could do, right? It's artificial intelligence, right? So supposedly. So it's what we're trying to do. We're trying to get to models that are super smart. Okay. Now, if you look at unsupervised learning, okay, so clustering, topic modeling, etc., they're not as clever, okay? So they get you kind of halfway. So let's cluster those samples, let's build some topics, etc. But this is not as sophisticated as a human could really do if they apply themselves to the problem. So they're good at building some level of modeling, but they don't go as far. They're not as crazy as the supervised learning algos. Okay. The good thing is about them is you don't need a lot of data, right? Remember I showed you the iris data set in the previous session. The 150 samples for different types of iris flowers. Well, you could apply clustering to that, right? You can apply clustering to 150 samples, and you would clearly see those 3 clusters. So, interesting for other problems. Now, we have 2 blank areas. What about those? So, this one, I'm afraid, is not really appealing. Why would you go to the trouble of building a huge data set to get unsophisticated models, right? We want to be in the top right corner. We don't want to be in the low right corner. Okay, so I don't know. For now, we don't see much happening there. And then there's the other one. Okay, can we build complex, sophisticated models with little data, right? Little prior data, and potentially no prior data at all, right? Figuring out data as we go. Like, that sounds like a weird thing. But that's what I'm talking about. It's the last session of the day, so I can be weird, right? Let's step back from machine learning. Remember this, right? For me, it's a century ago, but some of you, it might be closer. How did you learn to ride a bike? Did you have a labeled data set? Did you have like a family history book telling you this is how your dad did it, this is how your mom did it, and this is how grandpa did it? And no, of course not. Okay? So no labeled data to learn from. Did you get unlabeled data? I mean, did you watch videos of people biking? I was like, yeah, it's unlabeled, so no, okay, I can look at it and try to learn patterns from it. I don't know. I don't think anyone did that. Yeah? All right. Okay, actually, yeah, it's a good point. You could say, watching YouTube videos is probably a good way to learn new stuff, then trying to apply it to manually. But I would say generally, okay, probably the best thing you got at that time was, mom and dad telling you, okay, honey, so you need to keep pedaling and pay attention to the steering and look in front of you because you don't want to hit the tree. Okay, and that's like, yeah, okay, I can do this. And like every other kid, of course, you would fall down after 5 meters and cry and it's like, okay, that was nice, but okay, you do need to keep pedaling. Oh, okay, I got that right now. Okay, and then you try again, you pedal a little more, and 10 meters, you go 10 meters further, and then you forget about the tree or the car, because and you fall again. Okay, so it's a cycle of exploring, right? Taking actions and getting some kind of reward for those actions, for that sequence of actions. Pedal, 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 steer, 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 look, 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 steer, steer, pedal, pedal. Okay, so positive rewards, not falling, I guess, and hearing mom and daddy cheering, that's positive, and sometimes negative rewards, hitting a tree, falling in the river, all the things that kids do, right? All right, so sequence of actions, sequence of rewards, exploring, trying to improve as we go, right? Okay, let's keep that. Yeah. Remember this? Same story, right? How did we learn to do this? You could say some never learned. Some are still trying to learn. But it's the same story, right? There is no data set. Okay, you could read books on, dating and finding the love of your life. Okay, those are generally a waste of money, I guess. So, you kind of explore, take some actions, get negative rewards, slaps in the face, get positive rewards sometimes, and adapt and try to improve. Okay, so this is exactly what reinforcement learning is. Okay, you start from scratch, take actions, get rewards, right? After potentially each action, see if that's positive or negative, and then learn from that, and then try again. Trying to be a little smarter this time. Learn again, etc., etc. And it's a repeated cycle of exploring learning, exploring, learning, exploring, learning, right? Hopefully getting better each time. So now, of course, we didn't have a labeled data set back then, and we managed to learn, okay? How did we do it? And can we apply this intuition to machine learning? Well, yes, okay, so now in machine learning terms, we have an agent, okay, an algorithm, okay, so you can see yourself as an algorithm, that's okay. And we're trying to interact with an environment, okay? So it could be a real world environment, it could be a simulated environment, we'll talk about that. But okay, we live in this environment, we take actions, okay? So each action is going to modify the state. Okay, let's say I'm trying to move around in that maze. I take a step forward, obviously my position has changed, so state has changed. I can observe the new state and I can get a reward. Okay, so getting closer to the end of that maze, to the exit, is probably a positive reward. Getting lost is probably a negative reward. Falling in a pit is definitely, the end of that episode, as it's called. Okay, so that's the exact same thing. The agent explores, it takes actions, it gets rewards, okay, and the rewards are computed by a user-defined function, okay, that it's called the value function, the reward function, it has plenty different names. And that function literally outputs a number. Okay, so positive numbers are positive rewards, negative numbers are negative rewards. Okay, so looking at the state, oh, you fell in the pit, okay, you're dead. That's negative for you made it to the exit. Okay, positive reward. Okay, but you could say, okay, taking a step and not falling into a pit. Okay, that's kind of a mildly positive thing. You're still alive. You can keep going, right? So you can have very positive, very negative, or all kinds of rewards in there. And so the goal of that agent is to go as far as possible and learn over time to maximize the accumulated rewards. Okay, so the sum of rewards that you get for that sequence of steps, that sequence of actions, we're trying to maximize that. Okay, and so that's where we're going to try and learn. Initially, we will explore pretty much at random, do all kinds of silly things, learn a little bit from that data, and try again, and learn a little more, and try again, and learn a little more. And hopefully, if we get it right, if the algo gets it right, it should become clever pretty quickly. So stepping away from machine learning again, what can you do with this? Why is this an interesting machine learning technique? So if your problem is well defined, if you can build a long-lasting data set that will be useful again and again and again, supervised learning might work, unsupervised learning might work, okay? Classifying dogs and cats, okay. 50 years ago, a dog picture was a dog picture. 50 years from now, if we're still around, a dog will still be a dog, right? Might be a mutant dog, but it's still a dog. Okay, so those things are stable over time. The environment, figuring out animals, that's not very complex, okay? Now, look at things like supply chain management in a large company, or HVAC systems, right? The HVAC system for this building. If you want to train it to have the optimal temperature or the optimal power consumption, what does the data set look like? If you have 500 people in the room or 10, there's a big difference. Yeah? So you could say, all right, let's train for extremes. Now, what about 250 people? Okay, so what about the external temperature? What about? Okay, so we have the intuition that for some of those cases, like robotics, autonomous vehicles, etc., the environment is too complex, too dynamic, too chaotic to be described in a long-lasting data set. So let's not even try to do it, okay? So let's use reinforcement learning to discover the environment and adapt to that, okay? And we can do that now, and we can try again, we can train again next week, and we'll train on demand and adapt to the changing environment. As it turns out, this monster truck here, you don't get a sense of scale, but these things are probably, 10 meters high or something, and they're huge. and they can carry 250 tons of rock. Imagine that, it's a huge truck. These are autonomous trucks today. They are live in production. Caterpillar is running that thing. There's a video there. You can check it out later. And you can see those things moving around, and no driver, right? So, because the mine changes all the time, the layout changes all the time, the road condition changes all the time. So they train them, and then they turn them loose, right? That's a scary thought. So let's take a simple example. Let's go back to that maze navigation again. So you start in a maze somewhere, obviously. So that's the environment, and you don't know what the maze looks like. Otherwise, of course, it's not fun. So you're in an unknown location, in an unknown maze. The only thing you know is, okay, I can go forward, backward, left or right, but I can't go through walls. So these are my actions. They're well defined. So initially, I'm going to, move around at random. Okay, I'm just moving one step at a time, getting a reward. Okay, so maybe stepping in like I said earlier, stepping in the dead end is a negative reward. Falling in the pit is a negative reward. You could say, okay, I'll give you 100 steps, right? So you can take 100 actions, and after that, if you're still lost, okay, we consider that that's a failure. Okay, to put some kind of limit on exploration. Okay, and of course, getting closer to the exit or getting to the actual exit is a positive reward. So again, we decide what the maximum number of steps are. Okay, and that's what we call an episode. And initially, we're going to, like I said, move at random for a certain number of episodes, and that builds a data set in a sense. Okay, let's say we run for 50 episodes of 100 steps. Okay, so now we have 50 sequences of action, reward, action, accumulated reward, action, accumulated reward, etc., etc. Okay, and again, initially it's going to be terrible. But by training on this, by training the algo on this, the next time around, you can be a little smarter. Okay, and again and again and again. So the key thing to understand is we are not training on a pre-labeled set of mazes, right? We could have mazes with the actual path to the exit. Say, okay, learn this, learn this, learn this, learn this. That's not what we're doing, okay? We're discovering one step at a time for a number of episodes, and then we train on that part. Okay, this is what we've done. This is the rewards we got. Okay, learn from that. Okay, and this is really central. This is really how RL differs from everything else. You start with no prior data set. You explore and learn and explore and learn and explore and learn, hoping that the algo figures it out. So it's a little bit magical, I think. Right. Okay, you get that? This is the probably single most important thing. So the environment, like I said, is the space in which the agent operates. So it could be a real world environment, or it could be a simulator. Okay, so if you're training a vacuum cleaner, right, a robotic vacuum cleaner, no names, to move around, okay, the risk here is quite kind of low, right? So that thing could hit the wall 100 times, and okay, we'll learn. No one's gonna die. It's fine. Okay. You would need to rearrange the room to have many, many different combinations. But okay, you could say, right, let's use the real world environment. If you're training autonomous vehicles, I don't think you want to train on roads, right? So you want to train in a simulator, okay? But you really have the two options. So that the simulator, and probably for complex things, it's going to be 3D simulators that mine, those mining trucks that I showed you, they are trained on that 3D simulator with a 3D model of the mine and the roads, etc. So it is actually very advanced. I mean, I think building those simulators is in itself a huge thing, right? But it's the only option if there is some kind of risk to human life or human safety, okay? So I'll show you a few examples. So the next important concept before actually going into the demos is that trade-off between exploitation and exploration. So imagine, okay, we have a mouse agent, right? And it needs to explore that grid, and a number of things can happen. Okay, so find that small piece of cheese, which is a small positive reward. Move to a blank cell, okay? Nothing happens, I guess 0 reward, okay? Get to that electric shock thing, which meaning, okay, maybe you either you die or, it's unpleasant, okay? So negative reward. And of course, if the cat gets you, you're dead, okay? That's the end of the episode, so you don't want that. And if you're clever, you're gonna hit the cheese jackpot and get a very, very high positive reward, okay? So, you could build many strategies, right? Even without talking about RL, right? You could say, well, I'm going to explore, and I found that piece of cheese, okay, and I could possibly loop here, and it's always positive. I don't die. I make it to the end of the episode with some kind of positive reward, but you never hit the jackpot, okay? Or you could say, I'm going to explore like crazy, but hey, every now and then the cat is going to get me, right? Or I'm going to get electrocuted or something. So that's the trade-off. Exploitation is rely on what you know, right? Not trying to learn anything else. And exploration obviously is I need to take a chance and learn new things, right? So if you have a strong bias towards exploitation, you're going to loop here. And you will never get to the high rewards. So the sophistication of your model is not going to be great. If you favor exploration, then that mouse is going to run around like crazy, but it's going to find the cat pretty often. Okay, so that's part of what those RL algos do. Probably initially you need to explore, you need to move, you need to figure out what the environment looks like. Okay. And for some algos, actually, we will start for a bunch of episodes. We will just explore at random, with no meaningful strategy. It's called the heat up phase because we need to generate the data sets. Okay, so sometimes we'll actually get to the jackpot, and sometimes we'll actually get eaten by the cat. But we're exploring to just to understand what the environment looks like, and then, as we train, probably we'll do a little less exploring and a little more exploiting, and okay, that's the secret sauce in those RL algos. Okay, and a lot of them are off the shelf, so you don't have to worry too much about those for now. So now, how do we train those things? So remember what I said for machine learning. What's your business problem? Well, guess what? Before you start with RL, what's your business problem? Okay, what are you trying to figure out? And I would say more importantly, why doesn't this fit into the supervised learning or unsupervised learning scenario? Are you going crazy with this, or is there a strong need to use RL? Because RL is newer, it is harder to understand, etc., etc. So you need to define the goal. What's the objective? Okay. So I want the trucks to drive I want the trucks to pick up rocks and dump them here without killing anybody and falling off the cliff. Okay, that's pretty much the high level objective, right? What does the environment look like? So it could be simple. If you have a simple maze, if you're a mouse, life is pretty simple. If you're a 250-ton truck, life is more complex, and you need a complex simulator. Okay, really close to real life. Define the initial, what is the state? What's the state that the agent will influence? So for the mouse, it's very simple. It's the coordinates, okay, and that's it. And how much cheese did I find? For a truck, it's going to be the position. It's going to be lots of things. Okay, so complex. What are the actions you can take? And they need to be explicitly defined. There's no, there are no undefined actions. Okay, this is the list of things you can do, right? And how do you compute the reward? Based on that action that you took and how it modified the state. Okay, you took a step, you fell off the cliff. Well, that's bad. Okay, you took a step and you dumped the rocks in the right place. Okay, right, well done. That's what we wanted. Okay. Okay, now Define the environment. So are you using a real world environment or a simulator? There are some open source simulators for robotics. We launched a service called RoboMaker, AWS RoboMaker. That is, it's a 3D environment to simulate robots. Okay, and there are some commercial simulators. You could use MATLAB. You could use other things. Define the presets. So what does the initial environment look like, etc., etc. And then you write the training code, or you use an off-the-shelf algo, which is what we'll do tonight. And you write the value function, which is probably the single most important thing, because this is really what you're going to learn from. Okay, you did this. Here's the reward. Okay, this is the key thing. This is really the key thing, and we'll look at some examples. And then you can train, and training really means exploring training. Okay, so it's not just train once and done. It's okay. Kick things off. Let the agent explore, gather some data, learn from that, and cycle for a number of rounds. Okay, so this is pretty much what SageMaker RL lets you do. So don't look for the SageMaker RL console. It's part of SageMaker. So after all those SageMaker talks today, now you know it's all based on containers. So we basically add additional containers, additional environments for reinforcement learning frameworks. Okay, I'll show you the stack in a second. And it's a combination of a deep learning library and an additional framework. And we have support, like I said, for simulators, so RoboMaker, open source simulators, or commercial simulators. Okay, so that's, I'm sorry, it's not a great picture. This is the best I could find for now. So, like I said, it starts from a deep learning framework. From the machine learning perspective, the actual training process is running in TensorFlow, MXNet, etc. Okay. But what you're really doing is you're using one of those reinforcement learning frameworks. So this is Coach. It's an Intel framework, or RLlib. That's another one. And this is where the RL algos are actually implemented. Okay. So the names you may have seen are, DQN, PPO. Those are like I would say the popular ones that you'll see in all those tutorials and blog posts. Okay, and I'm not going to go into how they work because that's too much for this session. Okay, so, and these run on top of TensorFlow or on top of MXNet, right? So, like an extra API. And then we need simulators. Okay, so the de facto standard for this is a project by OpenAI called the GYM. So this provides 2D and 3D environments. Have you seen this one before? Let me show it to you. This is probably the best way to get started. Surely you've seen those examples. See, so learning to play Space Invaders, and so 2D environments, 3D environments. Okay, so what the GYM actually provides is that 3D model. Okay, so you don't have to go and code this. You actually write the code that learns from the environment. Okay, so the 2D, 3D part is already implemented. Okay, and these are good problems to start with and to get familiar with reinforcement learning. Okay, and then you can go crazy. But I would really recommend going through some of those tutorials. Okay, so that's what the GYM does, and of course, people have built on top of this, right? And like I said, you can use Sumerian, which is another AWS service for 3D, RoboMaker, the simulator, open source environments, or commercial environments. Okay, so I'm quite sure out there you have companies building 3D simulators for complex worlds, and again, the Caterpillar video kind of shows you what they're doing here. Okay, and of course, because it's SageMaker, you have plenty of notebooks to start from. Okay, and I'm going to run a few of those. Okay, so bottom line, what you're going to see in those notebooks is pretty much what we've been doing today. Grab a built-in environment from SageMaker, set some parameters, We won't have to have any data set because there's none, okay? And just go and train, see what the results are, okay? So the first one I'm going to show you is really Hello World example. It's called the cart pole. And the cart pole is actually one of those examples we saw on the gym. Can I? Yeah, I need. Okay, it was here. Yeah, it's that one here. Okay, so you have a cart that can move left or right, and it's trying to balance a pole on top of it. So obviously you have, there's a physics model behind it. So if you keep going left or if you keep going right, the pole will swing and fall. And the game is to obviously avoid, yeah, here it is, okay? Avoid tipping that pole one way or the other. Okay, so the only two actions are you can go left and you can go right. Right, so intuitively if we go left, that's going to fall. If we do the same thing on the right, it's going to fall. So that agent has to understand that it needs to go left, right, something similar, okay, to avoid that pole from swinging too far. Okay, so this is what it looks like. Again, this is part of the SageMaker collection. There's a folder for RL, and that's where those things are. Okay. Okay. So here this environment, okay, the 2D physics environment is provided by the OpenAI Gym, so I don't need to worry about this. So I'm going to import all kinds of libraries. I need an S3 bucket because I'm going to dump some logs and some images to visualize what's going on. Okay, IAM role, blah, 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 blah. Okay, and here I'm going to use again an algo. It's called clipped PPO. You don't want to know, okay, for now. And it's one of those RL algos from implemented in OpenAI. Okay, so trying to be clear. So what the algo does, okay, the algo is the agent. So the algo, you just tell the algo, these are the actions that you can take. You can go left or right. And every time you take an action, you change the state. So in this case, you change the angle of the pole and the velocity of the pole, right? And so I'll give you that, okay? I'll give you that state every time you move, and I'll tell you if the pole fell, okay? So that the algo works only on that, okay? It knows it can go left or right, and every time it moves, it gets a state which has 4, I think, dimensions. I think it may have pole angle, pole momentum. It's got a few things, but very, very little values actually, very few values. Okay, so I need to set some parameters for that algo. So how many steps will I train on? How many episodes will I use for training, etc., plus learning rate, a few machine learning things. And you can read all about it in the OpenAI Gym, but these are really default values. You could stick to that, okay? And ignore everything else. So again, the key thing is, and yeah, this is the important bit, so we use that pre-built environment, okay? And that's about it, okay? And we have some boilerplate code that SageMaker will run to get everything going, okay? But it's really more configuration than anything else. All right, so the only decisions that we made here are, I'm going to select this pre-existing environment, which has a pre-existing list of actions, and I'm going to pick that algo, and it's going to try and figure it out. Okay, so it's all, like I said, it's Hello World. You really don't write any code in this example. It's just to see the whole workflow. And I'm going to use the RL estimator object from the SageMaker SDK, passing that boilerplate code to get everything going, saying, okay, you're going to train with the coach environment, the coach library on top of MXNet, and you're going to train on one instance, and that's about it. Okay, so the typical SageMaker workflow still applies. Select a container, select the infrastructure you want to train on, and go. Okay? And then we train. And let's grab, I don't know why the training log is not here, so let me grab it from, it's probably on the next page. Here we go. Yeah. Okay, so the config files make it a little difficult to understand because there seems to be lots of stuff. But again, in a nutshell, we have an environment, right, with a state that has a couple of dimensions. We have two possible actions, and we have an algo trying to figure it out. Okay, and that's what the training log looks like. So let's just take a quick look. Okay. All right, so okay, so we're starting to, initially we're just exploring. We don't really know what we're doing, so we train. We start completely from scratch, zero prior knowledge, and the agent will, the algo will move around and say, okay, go left. All right, go left. So the state is modified, and I guess if you go left, the pole will tilt a little bit to the right. Okay, and then maybe go left again. All right, it's going to tilt a little more. Okay, and maybe go right, etc. Until that thing falls. Pretty much, that's the end of the episode. And so we see those different episodes happening. So we only ran for 12 steps, so that wasn't great. And we train. So we learn episode by episode, right? So it's like, okay, probably we went 12 steps to the left, and of course that thing fell. So next time around, we try to be a little smarter. And you can see, well, this time we managed to take 25 steps. 37, 109. So it's actually learning pretty quickly, right? It's like, yeah, I can do this, right? So after every iteration, it learns, okay? And then we run evaluation, so we measure performance, and then we go back at it, okay? So we explore and train again, explore and train again, explore and train again. And you can see the number of steps is going up. Okay, so we go further and further every time. Sometimes we go quite far, right? But the reward is not really high because maybe we barely made it, right? It's like, oh, we went a little bit too, maybe we almost tilted that pole. And that's probably a negative reward. So it's like, guys, you went dangerously close to actually topping that thing down. So don't do that again, right? So the reward could be, it doesn't have to be +1, -1. It's like, yeah, you're super safe. Ah, man, you're tilting too much. Nah, don't do that, right? That's the dangerous behavior. So go back into that safe zone. So that's why the reward is not correlated strongly to the number of steps. Okay, and it goes on for, the number of episodes that we define, and we can see, we keep going further and further and further. Okay, so we're learning how to do this. Okay, and again, that's the algo doing it. We didn't write any code, and it runs to completion. We can plot the rewards for the episodes. So the accumulated reward for a given episode. And of course, initially we kind of suck at it. And I'm not sure what happens at episode 130 or something, but we get clever all of a sudden and say, oh, well, we find the secret to balancing that pole, and the rewards improve massively. So it doesn't, we do something silly again, okay? And you can see probably that's the trade-off between exploration and exploitation. So probably, here we're really favoring exploration, trying to figure out all the possible combinations. And then at some point, the training algo says, okay, enough, right? I know enough. Now let's exploit what we know. So we do a terrible mistake here, and then we stop learning. But we see this massive jump. So we got clever here, okay? And we could, a cool thing in the gym is you can actually grab pictures and you can visualize a given episode. Okay, so this is what it looks like. So here it's kind of okay, right? We seem to have learned, and it's looping. Okay, it's not a never-ending episode. It's looping. So it looks like we learned that. Okay, go a little bit to the left, go a little bit to the right. Never tip that thing too far, because that's dangerous, even if it doesn't fall. And find this balance movement. Okay. And we completely learn this by exploring and then exploiting. Okay? So that's what makes the gym cool, is you can see what's happening. Okay? You can play Space Invaders afterwards if you want to. It's the same thing. Okay, so let's try another slightly more elaborate example. So it's the knapsack problem. So that's going to take you to your university days. Remember that problem? We have a knapsack, or a bag. It has a certain volume, a maximum volume. It has a maximum weight that you can take. And we have a random stream of parcels that come, and each of them has their own shape, their own weight, their own volume, their own weight, and we're trying to fit as much stuff as possible as we can. Okay? And now the actions are, okay, when the next parcel comes, you can decide to put it in the bag or to drop it. If you take it and put it in the bag and it fits, that's a positive reward. If you take it and it doesn't fit in the bag, that's bad. That's a negative reward. It's like, whoop, wrong decision. And if you decide to drop it, it's also a negative reward, but probably a less negative one. It's like, now, ignore this one. Yeah, this one should fit. Yes, it fits. Good call, right? Picking one and trying to fit in, it's like, that doesn't fit. Okay, that's bad judgment. So this is probably bad. Okay, so again, we're gonna use coach. So the problem statement, the environment, the actions, the state, all of that stuff needs to be carefully defined, right? So import all of that. Okay. Setup. We're using the same algo. It's pretty much very similar settings. So let's ignore that. That's again boilerplate stuff to get things going. The estimator is the same. This time we use TensorFlow. So you see SageMaker is not standing in the way here. It's just helping you train that thing. So this time what is actually different, let me grab that code, is that we build a custom environment. Okay, so we don't have a simulator for this. We actually write Python code that will manage the environment. And we've all done this one, right? We've all done this in college. It's a simple environment. It's a bag, like I said. Okay, so the bag is a capacity. It's either full or not, right? And that's the state we're managing. Okay, so having a custom environment doesn't have to be super complicated. Okay, the environment is how much capacity do we have left in the bag from a weight perspective and a volume perspective. So we initialize this, okay? These are the default values. And this is the step, okay? So this is what, so once the algo takes a decision, this function is gonna be called, okay? So the algo decided to grab the package and put it in the bag. Okay, well, so if the action was throw the package away, okay, well, there's a penalty for that. So the reward is a negative number. If we decide to put the package in the bag, then we need to make sure it fits. Okay, so we're going to compare the remaining capacity to whatever that parcel means. If it fits, that's really cool. We get a reward for that. If we actually made the wrong call and we have to drop it, then there's a penalty for that. Okay? So that's the environment. That's the simulator. Okay, look at the action, figure out if this is a successful or unsuccessful action, and return a reward. Okay? If we fill that bag, right, then we're done. Okay, and that's it. And we just update the state. Okay, so this is the new capacity, this is the new weight, etc., etc. And this is what we return to the algo. You did this, here's the new state, here's the reward. Exactly what I explained earlier, hopefully. Okay? So you can actually, by writing that simple, seriously, freshman level code, okay, you can solve complex problems. Okay? It's all about looking at the action, modifying the state, computing a reward, returning the new state and the updated reward to the algo. And whatever that clip PPO guy does, okay, we ignore it for now. We're not into writing RL algos, we're into using RL algos. Okay? And I don't think anyone here wants to write RL algos. Okay? So same story, we're going to trains for a bit. I'm sure we would see pretty much the same thing in the training log. Okay? So learning and etc., etc. We can plot the rewards. And I'm not so happy about this one, right? I'm not sure why I left it like that. I didn't try and run it again. It's not what you'd like to see. You'd like to see terrible decisions going up, right? And here it looks like we're not learning much. So either we're not plotting the right thing, or I got something wrong, or this is a weird training. I don't know. I need to investigate. But this one looks weird to me. Maybe I'm just an idiot. That's the number one option. Okay. And we can visualize. So there's a bit of visualization code as well. So unfortunately, I couldn't be, I couldn't save my life if I had to, and by writing this. But here, and this is going way too fast, but you could actually go through episodes and see what decision that thing is taking. Okay? Which I think is important, because we're trying to get to human-like decisions. So I think it's important to look at episode and say, okay, with this bag and this parcel, what decisions would I take? Would I drop it? Would I try to fit in? So here it's going way too fast, but we see volume, we see the rewards, we see the weight, the volume capacity, we see the weight capacity, and yeah, it's definitely filling up the bag. Okay, but is it always the optimal decision? I think it would be worth looking at this in slow motion and see if the algo is actually making the right calls. Okay, but it seems to fit stuff, right? And the rewards, they are positive, not great. I don't see a trend line. Maybe there is a kind of a weak trend here. I don't know. It's hard to say, really. Okay. So this is another example. We're still using the gym, or we're still using OpenAI. We use a custom environment, which is really, maybe 100 lines of Python, not really complicated, and we use a pre-built algo. Okay. So you could clone this notebook and adapt it and solve some complex problems. And the last one I want to show you I think is interesting. Here, maybe you saw during reInvent, we actually launched predictive auto-scaling for EC2. So up until now, you would have to, if you wanted to scale EC2 capacity, you had to define thresholds and alarms and scaling policy, etc. And now you can click the button that says, no, ignore all of that and be smart and use a machine learning model to predict my EC2 capacity, right? Go and look at it. It's pretty cool. So here, of course, I'm not going to reveal the actual implementation. This is a toy implementation of a similar problem. Okay, so the business problem we're trying to solve is this. Okay. So let's pretend this is my traffic. This is what my traffic looks like. And if you guys run websites, a lot of it looks like this, right? Very busy during the day, not busy at all during the night. Maybe that's Sunday and maybe that's Monday. Some variations across cycles and some spiky behavior, right? This one, yeah, like this, right? Spiky things that drop down again. Okay. So here, there's a bit of code that actually generates those things. So the simulator here is basically some Python code that generates those traffic loads. Okay. So it generates a full series here, but it's going to feed it to the model time step by time step. Here's obviously there's a time dimension. So it's not the agent moving or the agent doing things. It's the agent receiving the next time step. Okay, so let's say maybe there's a step every minute or every 5 minutes. Okay, so here's the new load What do you want to do? Add instances, remove instances, or both? Which is weird, but we actually let the agent do that. Okay? Right? So you start with some baseline capacity of instances, and then you ask the agent, based on the workload that it sees now, what do you want to do? So it decides, you compute a reward. If you are under-provisioned, you're losing traffic. That's very, very negative. If you are over-provisioned, you're just wasting money, so it's negative, but not as much. And if you're just right, you get a positive reward. Okay? And the state is pretty much the number of instances you're running and how that relates to the number of transactions you can process, etc. Okay? And it's the same, if you look at the code, it's actually not scary, I think. That simulator. Here it is. So same as the knapsack, we have the auto-scaling simulator. So it generates those profiles, right? But more importantly, we have that. So it needs to react to load. That's the one. Okay. Oh no, sorry, that's the step. Okay. So what do you want to do? How many instances do you want to add? How many you want to remove? Okay. So we look at that, and then update. There's a warm-up thing. It's kind of realistic. It's like it takes a few minutes to actually put those instances in production. So it's kind of nice. And okay, based on this, now you react to the load, and that's where you compute the reward. Okay, so if load is fine, then okay, we have a positive reward. If we lose some transactions, that's really, really bad, and we get a negative reward. Okay? And again, what you return back to the algo is always the same thing. It's the updated environment, and so the number of running instances and the reward. Okay, and it goes and it does it again and again and again and again. Right? And this is the actual code that generates those steps. So it's, as you can see, it's not a lot of code. It's not complicated. So same old, same old. I suspect we keep cutting and pasting the same file here. Right? We train, still using Coach, still using TensorFlow. And okay, we train for a bit, right? And it's the same story. We train, we explore, we train, we explore, we train, we explore, we train. Okay, and after a while, we can plot. And this is actually an incomplete plot, so let me show you a longer example. Where's that blog post? Yes. So if you plot everything, you see this. Oh, come on. Okay, so initially we see the exploration yields terrible results. Okay, and those are normalized values on the left, but the rewards are terrible. It's like minus 10,000 and et cetera, et cetera. So initially we do a terrible job, and then we start to improve. And then you can see we can consistently hit positive rewards. Okay, and there's a tiny upwards trend, right? So we could probably keep improving a little bit. Okay, so we actually figure out how many instances should be started or stopped at each time step. Okay, and once again, the agent, the algo, doesn't see the full profile, right? It just gets, it just gets the next step, okay? So here, obviously, we generate those things for the full duration of the episode, but the agent at any given time only sees the next data point. So it cannot say, oh, this is sharply going up, so let's fire up 10 instances and I'll be fine, right? So now this is going up nicely, and there's a spike here. What should I do? Should I wait? Should I weather the storm? Or should I actually start something that's going to be not needed 10 minutes later? Okay, so it just sees the next data point. That's the thing. And if you zoom in on the last few iterations, that's what you see. And you can see it is slightly going up. So this is a more complex example because we can take two actions. We can take two actions at the same time. We have a warm-up time, so we actually take an action that doesn't have immediate consequences. Okay, we take an action that actually helps 5 minutes later, so we need to anticipate that, but we managed to learn this. Okay, we managed to learn this. So I think this is a pretty nice example. And again, you can read this Python code quietly, and you'll figure it out completely. Okay. All right. Okay, here we go. And the last thing, okay, I mentioned it this morning, but I want to give you a few more details. So, of course, I would recommend you read about the OpenAI Gym, run the examples that are over there. You can run them on your laptop, and then run the SageMaker notebooks and learn some more. But if you really want to have fun with RL, we released that Deep Racer car at reInvent. It's you can pre-order it. Hopefully, we'll be able to deliver it in Europe really quickly. There's a YouTube video here. Where's my? Is that working? Oh yeah. Here we go. Oh no, now I'm lost. Okay. This is
Welcome back to Innovative Feedback to Las Vegas. We're live on Twitch.
So here's the car. No, I wanted to show you the racing car. Come on. That's the one. Yeah. So this is the actual event. The actual workshops that we did in Raymond. So we have this track, okay? And you can simulate. So even if you don't have a car, you can use RoboMaker and run in the simulator. And then once you have a car, you can download your model to the car and put it on the track, and off it goes. Okay. And the only thing that you have to write is actually the reward function. Everything else is taken care of. So we keep it really simple. Just write the reward function, and it's I'm told the top one today, the fastest one is the one that runs the fastest car is 15 lines of Python. So it doesn't have to be a lot of code, right? So there's hope. There's hope. Okay, so this is going to be available in Europe in the next few months, I hope. We're going to race those at summits. We'll have a track, etc., etc. So there's a Deep Racer League with the summit races and finals at reInvent last year. Okay, so try your luck. You never know. Okay, so if you want to learn more. Same URLs as before, the SageMaker page, the Deep Racer page, and the SageMaker notebooks if you want to run all that stuff. These train for, these are really short to train. These are simple examples. So they're not going to be costly at all. All right? All right, that's the end of a very long day. If you have questions later on, you can, like I said, you can ping me on Twitter. It's a good way. Or connect on LinkedIn. Send me feedback, questions. Always happy to help you out. And so you will get all the slides in the next few days. You should get an email from my marketing colleagues, and everything was filmed. So if you're if you want to suffer through the whole thing again, it should be on YouTube pretty soon. All right. So thank you very much. I hope you had a good day with us, and thanks again for sticking with me all the way. And see you next time. Right? Thank you very much.